Hi everybody. This is a video that's going to hopefully help you figure out how to do what we call a linear regression to determine the molecular mass of DNA fragments in a gel. What that really means is we're going to take a picture of a gel, we're going to analyze it, and we are going to determine using some information from the ladder, which we've purchased. We're going to use this lane of DNA to help us figure out the sizes of DNA fragments in this lane, and this lane. So without further ado, I want to let you know about one ground rule that I have. I'm going to ask you at certain points to stop the video, hit pause, and do what I ask you to do, and then hit play again. And just so you know, I have given you pieces of paper and rulers. I want you to know, I know you can't see it, but I have paper and ruler. So I'm going to be doing the same thing you're doing, hopefully in the same time you're doing it. But I'll edit out that part out of the video so that I'm not wasting your time while you're doing it. So I've written 4 rules or 4 steps to make this happen. And I hope that they're going to make sense to you as we go. Okay? So without further ado, molecular mass determination of DNA fragments. And the first thing we need to know when we're looking at this gel is where our molecular weight ladder is. In this case, it's in lane 5. So lane 5 is full of DNA fragments that have been allowed to electrophoresis. Remember, we loaded all, it looks like lane 2, 3, 4, and 5. We left 1 and 6 blank. But we loaded DNA into 2, 3, 4, and 5, and all the DNA was allowed to run towards red or towards the positive side. And based on its size, it seems to have separated out. And as we talked about in class, the smaller pieces of DNA tend to run further, and the bigger pieces of DNA tend to run not as far. So this is a gel from a friend, and it's not the gels that we use, but it's analogous, and I'll be able to teach you about how to do this using this gel, and then we can use the same steps for our gels. So the first step is I'm going to ask you to measure the distance from the bottom of the well, or the top of the picture if we don't have wells, to the bottom of the band, here a line made with a pen. In other words, here's the bottom of a well. You are going to take your ruler and your piece of paper, because you have the same picture, and you're going to measure the distance from the bottom of the well to the bottom of every single band that you can see in this picture, starting with the ladder, but then you can go to lane 4 and then lane 3 and then lane 2, and you should record that someplace safe that you know, okay? So when you measure it, you're going to basically take your ruler, set it to the bottom of the well, or if we don't have wells in the picture, as you'll see in a little while, possibly, they might get cut off. You can just take it from the very tippy top of the picture, but take it, in this case, because we have the well, take a measurement from the bottom of the well, set that to 0 millimeters, and see how far this piece went, 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 and so on for lane 5, and label that as lane 5, and then lane 4, and label that for lane 4, and lane 3, label that lane 3, and lane 2, label that lane 2, okay? And the measurements have to be in millimeters. All right, so I'm going to take a few minutes and do that myself now, and you are going to do the same thing. So hit pause, really hit pause, and make those measurements. Welcome back. So this is what I at least got from my piece of paper. I got down to this first band, the bottom, we made that little line for you. 25 millimeters, the next one was 28, the next one was 30, the next one was 34 millimeters, 37, 40, 44, 49, 52, 57, and 64. And you should be in the same zip code, okay? So these were the ladder, okay? And I told you it was really important that you write that they're the ladder somewhere, okay? So we're going to record that this is the ladder. Why aren't you working? There we go. And then for lane 4, I had some different bands, some different distances. I can read them off to you. I got 24 for the top 1 millimeters, 28 for the second one, 32, 39, and 45, or maybe 48. I can't read my handwriting. Looks like 48, actually. 48 millimeters for this bottom band. And then for 3, I got 25, 29, 32, 39, 43. And for lane 2, I got 22 millimeters, okay? So that's all of them. But for right now, I really only want to focus on the ladder, and then we'll come back with these guys later on, okay? So the ladder, we know all these distances that it ran, and now it's time to pull out the piece of paper that has the molecular masses of each of these pieces of DNA. And if you look at the piece of paper, it's the manufacturer's instructions. It basically says that the bottom band is 500 bases. And the next band up is 1,000 bases, 1K. The next one is 1,500 bases. The next one is 2,000 bases. The next one is 3,000 bases. The next one is 4,000 bases. The next one is 5,000 bases. Be careful. The next one is 6,000 bases. The next one is 8,000 bases. That's what I want you to be careful. They skip some. The next one is 10,000 bases. And the next one is 15,000 bases. Okay? So from the manufacturer, they built these. They know how many bases each one of these bands is, and your job is to kind of match them up. Okay? And remember again, I can tell you in college I screwed this up. The furthest band is the smallest. In college, I wrote it that it was the biggest and everything else was backwards from there on out. So don't make that mistake. This furthest band is the smallest. Okay? So step 2, which was basically what we just did. We used the molecular ladder literature to tell you how many base pairs each band is and correlate that information. So from that piece of paper, we now know that the band that went 25 millimeters is 15,000 bases. The band that went 64 millimeters is 500 bases. And everybody else is somewhere in the middle. Step 3 is to create a graph of your standards, and we're going to call this a standard curve. And this is kind of interesting because everything about you that you've done for the most part tells you, well, what am I going to create a graph of? Well, it would be useful for us to create a graph of the number of bases, base pairs, on the y-axis compared to the distance in millimeters on the x-axis, okay? And that shouldn't be too hard. We're just going to have to set a scale and correlate 25 millimeters to 15,000 bases and then 28 millimeters to 10,000 bases. And you know what? There's a program for this. It's called Microsoft Excel, and I did it for you. So here's what it looks like. Here's the distance traveled, and here's the number of base pairs. And every data point that you see here correlates to the distance traveled in millimeters on the x-axis. You know, the scale is set from 0 millimeters up to 70, and from 0 base pairs to 16,000 base pairs. Now, there's a problem with this. And the problem is that this graph is a logarithmic function. It's an exponential situation. And it's a fine looking graph because you can see how nice, I put a trend line here so you can sort of, if you wanted to plot something on the trend line, you could. But the issue is it's really hard for us as high school students and even into college to either sort of interpolate, or it's even harder to extrapolate when you have a curved line. And what interpolation means is, well, look, here's how this graph is actually going to get used. I'm going to take another band from my graph. So let's take this band, and I have 24 millimeters. This band. Okay, I hope you have 24 millimeters too. So I'm going to take 24 millimeters. I'm going to basically say, all right, that's 24 millimeters. Well, where does 24 millimeters hit my standard curve? Well, it hits right there. So now from here, I can draw back to the y-axis and say, well, it looks like we're dealing with between 12,000 and 14,000 bases. And I would actually go so far as to say it might be about 13,100 bases, which is fine. But anything that's smaller than any distance that is smaller than 24 millimeters, it gets really hard to estimate what's going on up here, or anything that's bigger than 60 centimeters or 65 centimeters. It gets really hard to guesstimate what's going on down here. All right. And that's ultimately what we're trying to do with this particular graph. So this curved line makes it kind of difficult for us to make really accurate estimates here. All right. And that's a problem. So instead of having a curved line on normal graph paper, what if we instead took logarithmic graph paper and we plot the same data, but now what kind of line do we get? The answer is a nice straight one. And the cool thing about straight lines is it's easy to extrapolate from, I can kind of more or less guesstimate what's going on past the graph one way or the other. So if I have a piece of DNA that only goes 10 centimeters, I can guesstimate its size a little bit better. And if I have a piece of DNA that went 69 centimeters, I have the ability to graph with a lot more confidence than something that I have to extrapolate from a curved line. All right. So what that really boils down for us is I have to teach you how to graph on semi-log paper. And the idea is we're going to get a nice straight line from our standard curve or from our standards, and then we'll be able to use this to get some data from what we actually saw in the gel. And without further ado, here's something called semi-log paper. And here's our gel again. But here is semi-log paper, okay? Semi-log paper looks kind of wonky. And this is 3 series semi-log paper. You might be staring at 4 series semi-log paper. All it means is that if you look on the on the y-axis, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. And the higher up you get, the more compressed those numbers become. All right. And without getting too far into it, the way you have to set the scale on this is that the top number of one series, so 1 through 10, the top number becomes what the next series counts by. So if I was to set the scale here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the next series I'm going to count by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then the next series I'm going to count by hundreds. 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Now, our scale in terms of DNA pairs, which is what we are going to use as the y-axis, I think it's going to be easier to set the bottom scale on a 3-site series to tens. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So just set your scale so you can actually fit what the DNA base pairs is going to be so they fit. So that's the y-axis, and I'm going to actually pause it and put these in, okay? And you should do the same unless you don't understand what I'm talking about. And then in that case, let it keep running. And then when you see what it all looks like, then pause it and write it on your own paper. All right, so that's done. And in case you're wondering really why this happens, the answer is pretty simple. For every millimeter the DNA travels, it gets exponentially harder for it to move, okay? So basically, the further along it goes, it's encountering more and more and more resistance, and the only way to account for that is to sort of plot it out on an exponential piece of paper, which is what the semi-log paper is. And as I said before, you can set the scale on the left. I know it's really hard to read the writing here, but 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 2,000, 3,000, 4,000, 5,000, 6K, 7K, 8K, 9K, 10K. And again, the reason we set that is because the further the band goes, the exponentially harder it is for it to move. And also, with every 10 base pairs, oh boy, with every 10 base pairs, it becomes exponentially harder for those base pairs to move. What just happened? I think my computer might be possessed. Let's just erase all of this. No idea what happened. So that is what's going on with the y-axis. Now we got to deal with the x-axis. And the only way to deal with the x-axis, that's easy. That's just your number of millimeters, okay? And that really shouldn't be that hard. You just have to set an appropriate scale for yourself, okay? Why you gotta be like this? Hold, please. All right, we're back in business. So we're just gonna put on the bottom here millimeters, and judging from my picture, I got up to 64 millimeters. So why don't we make every 2 boxes 1 centimeter, which is going to be 10 millimeters. So again, I'm going to try and squeeze this all in. 10 millimeters, 20 millimeters, 30 millimeters, 40 millimeters, 50 millimeters, 60 millimeters, 70 millimeters, 80 millimeters, 90 millimeters, 100 millimeters, okay? Even though we only went up to 64. I guess I could have done, I might have been able to squeeze 4 boxes, but this scale will work for us, okay? So the next thing you do is just plot. My first band, if we remember from the previous picture, 25 millimeters, 15,000 bases. So we're going to go find 25 millimeters, which is here. We're going to go find 15,000 base pairs. Oh, which I can't because it's off the top. But you might be able to because you might have 4 log base paper. All right, let's go see if we can find the next one. 28 and 10,000. So we're going to find 28 millimeters, which is just smaller than 30, and that's 10,000 bases. So we're going to go all the way up, bada boom, right there. Then we're going to go back here and say, all right, 30 millimeters and 8,000 base pairs. 30 millimeters, 8,000 base pairs. That line right there. Then we're going to go back, and we're going to say 34 millimeters and 6,000 base pairs. And you should see by the end of this, I mean, I'm going to keep going. You can pause it, and why don't we come back together when all of this is plotted out on that particular piece of graphing paper. So go ahead and do that and pause me now. Pause me, really, pause me. All right, so welcome back, and I just did this. So again, that was 10,000, and that was about, what, 28 millimeter, 25 millimeter, or no, 28 millimeters. And then the next one was 10,028 millimeters. The next one was 8,030 millimeters. The next one was 6,034 millimeters. And so on and so forth, all the way down to here, 500 bases. And I kind of lined that up with the 500 bases. And that was 64 millimeters. So I came in just in front of 65. So lo and behold, you get this reasonably straight line. And I mean, that's pretty good for a squunched up semi-log piece of paper that I had to mess around with to fit on my screen, and a pen that has a really thick tip on my computer here. So what we just did was the most important part of the whole process. We graphed out our standard curve. And what a standard curve is just the line that your standards make. And what we can do is we can create a best fit line. And on the computer, it's pretty easy, but Excel will do it for you too. But you can take a pretty good, I mean, geez, it goes through most of those points. And as long as it gets through most of them, that's a pretty good point or a pretty good best fit line. Now, the difference between interpolation and extrapolation is something that a lot of scientists really care about. Interpolation means my best fit line should stop at my standard, at the end of my standard. So it should go, I have a data point here to here, and that's it. So what I really should do if I'm a good scientist is I should stop, there's my best fit line, the end. Okay? But the problem with that is if I have a piece of DNA that ran, let's say, 80 centimeters, I can't look at that piece of DNA because my line doesn't go down that far. Okay? It only goes to this 64 centimeters or millimeters. Okay? So I advocate for never extrapolating, but I also realize that sometimes we have to extrapolate. So that's why you saw me when I made the best fit line, I kind of extended it down here just in case we do have a piece of DNA that ran 95 centimeters, it's still on the line and we can figure out what's going on with it. On the other side also, I mean, you might have the 4-cycle paper, so you might actually have that 15K piece up top, on the piece of paper. You'd be up here where add-ons is on my graph. But the paper or the line would extend up there. So the next thing that we're going to do is we're going to use this line to figure out how big these pieces of DNA are. And I mentioned before that we're going to look at line 4, and I actually have the distances for most of these. So I'm going to take the bottom band, I got 48 millimeters. The second band, I got 39 millimeters. The band above that, I got 32 millimeters. The band above that, I got 28 millimeters. And the band above that, I got 24 millimeters. Okay, so that's all these bands here, and those are how far they went from the well. Okay, so what I can now do, and this is using the standard curve, I'm going to say, all right, my curve looks pretty straight, which is good, which means if I can go to 48 bases, and if I can guesstimate, well, 48 bases is right about here, between 40 and 50. And I'm going to put a line, or I'm going to put a little mark at 48, and I'm going to draw a line straight up to where it hits my standard curve, right there. And where it hits my standard curve, I'm going to draw another line from my curve. Oop, don't move that line. Let's draw another line. Please give me another arrow. I'm going to draw another line from that point to the y-axis. And as you can see, it comes in just under 2,000 bases. It actually comes under, looks like 1,800 bases. So I'm going to write down, because it fits my standard curve, that 48 millimeter base, that 48 millimeter traveling piece of DNA is 1,800 base pairs big. And that's a heck of a lot better than saying, yeah, you know what, it was a little more than 1,500, a little less than 2,000. I'm going to say it was 1,800. That's not scientifically accurate enough for what we're doing in this class and what you'll do in college. Okay? And you can do the same thing, 39 bases. So let's get a straight, and you have a ruler to draw this. So I would do some different colors. That's why you have different pencils, colored pencils at your desks or floating around there. So by 39, I'm going to go right here, just below 40. Make that go all the way up to my standard curve, right there. And then I'm going to make another line. I'm going to go from my standard curve here, and I'm going to say, hey, that's pretty close to 4,000 bases. So I'll say that 39 is about 4,000 basis pairs. Okay, does that kind of make sense? I hope. Now the issue is, remember the biggest bands were 10 and 15,000, and I am not going to get that 24 because that'll be off the graph. So let's take that 24. Try that again. 20, 30. So 24 is going to be right about here. Let's make that come all the way up. You see, I can't hit the graph. I can't hit the best fit line because it's off the graph. It might be on yours. I hope it is, but I'm not going to be able to get that 24 bases. So I'm out there. That 28, I should be able to get the 28. So let's move this thing over to 28. Yeah, that looks like it's about 28, and you'll see it's right at the very tippy top of the standard curve. So I would say that 28 is 10,000 bases. Okay, and that 32, let's do one more. 32, there's 30, so let's go to 32-ish. Have that go up, ba-boom. And then have another one right from there, go over. Oh boy, this is crowded. Between 6,000 and 7,000. Each of these little tick marks, I believe, is 200. So I'm going to say 6,600, 6,700. I think that's a pretty good guesstimate for being on my computer. 6,700 base pairs. Okay, so that's how you actually interpret the data that's presented to you on a gel. And again, we did only lane 4. I would love it if you guys could work on lane 3 and lane 2, and then we can get back together the next time we see each other and sort of see what's going on. All right, so that is the gel that's in front of you, and that took a heck of a long time. I'm going to ask next that you go to this next particular piece of, well, you got another piece, you should have another piece of semi-log paper. And this is a gel that you should have printed out. And there's also the manufacturer's instructions for this. And I will tell you right now that this lane is the ladder. Okay, and this is the smallest band. This is the 500 bases. So you have the manufacturer's directions, so you're going to have to measure from, you can barely see the wells up here. I'm not sure if they came out on the pieces of paper that you have in front of you. And if you can't see them, you can just measure them from the very tippy top of the paper. So tippy top of the paper down to here, correspond that to 500 bases, 1,000 bases, and so on and so forth. And then I'm going to ask you, so if this is lane 1, lane 2, lane 3, don't worry about lane 3, lane 4, lane 5, and then lane 6, you can tell me how big most of these pieces of DNA are, especially considering I know you should have the 3-cycle semi-log or the 4-cycle semi-log paper. So the maximum here is 10,000 bases. You should be able to tell me how big these pieces of DNA are using the bigger piece of paper. Okay. So without further ado, I hope that sort of made sense. And that's actually the last step of the 4 steps for doing this. We did step 1, we did step 2, we made the standard curve, and then step 4 is interpolate, which means stay within the curve, or extrapolate, which I don't like doing, but we sometimes have to do it by extending out that line for you to come up with the unknown bands. And the crazy part of this is there is a right answer. And when we get together next time, I will talk to you about how to find that right answer. Okay? So I hope this made sense, and good luck.